Well, welcome everyone. My name is Shelby Arndt, and thank you for tuning in to the USGS Landslide Hazards Seminar. This meeting is hosted by the Landslide Hazards Program and is co-organized with John Perkins and Jamie Kostelnik. You can submit questions via the chat window or use the raise your hand feature along with your microphone and video. And we will wait till the end of the presentations to take questions. In the meantime, please do your best to make sure your microphone is muted when you are intending to speak. Today, we have two speakers, Georgie Bennett from the University of Exeter and Francis Rengers from the USGS here in Colorado. And both Georgie and Francis are going to be presenting different flavors of landslide channel interactions in the Colorado Front Range. Georgie is thinking about landslide channel feedbacks during floods, and Francis is studying how channel form and in-channel features control patterns of debris flow, erosion, and deposition. So to introduce our speakers, Georgie Bennett is an associate professor in geography at the University of Exeter in the UK. She has a PhD from ETH Zurich and spent 4 amazing years doing postdocs with the University of Oregon and Colorado State University. She won the EGU Outstanding Early Career Scientist Award in Geomorphology in 2020, and her work focuses on developing tools to monitor and model landslide hazard cascades, including smart boulders. She is sorry she can't make it in person today, but she's happy to take questions via email, which is up here on the slides, and trusts Francis, who is a co-author on the work, to also answer questions at the end. Francis Rengers has worked at the Geologic Hazard Science Center in Golden, Colorado since 2014. He started as a Mendenhall postdoc and transitioned to a research scientist focusing on debris flow processes. Prior to joining the USGS, Francis spent time in the private industry working on reservoir sedimentation and river scour, as well as with the state government at the Colorado Water Conservation Board. And his work involves field monitoring, modeling, and remote sensing using LiDAR and UAVs. So since it's very late for Georgie right now in the UK, we're going to air her pre-recorded presentation first, and then we'll hear from Francis and take questions at the end for both talks.
Hello, everyone. Thank you very much to the seminar organisers for the invite to share our recently published research on landslide channel feedbacks, amplify channel widening during floods. Sorry I can't be there live, but it's great to be able to share this pre-recording with you. My co-author on this work, one of my co-authors is Francis Rengers, who I know is presenting after me today, I believe. So he should be able to take questions, but if you do have any follow-up questions, then please reach out to me by my email address, which is shown up here. So yeah, this work focuses on the geomorphic impacts of a large storm event in Colorado back in 2013. And we show with a combination of field analysis and multiphase modeling how landslides can amplify channel widening during floods. I just wanted to mention that we do have a companion paper, this one on the right here, which was part of a project that I led in the Philippines on simulating cascading landslide hazards, called the SCART project. And in this paper, we applied the same methodology I'm going to talk through today to a catchment in the Philippines that was impacted by a typhoon event. So I'll briefly return to this at points through my presentation, but I'm mostly going to focus today on this study from Colorado. Also worth mentioning, I started this study when I was a postdoc in Colorado back in 2015 with Sarah Rathburn at Colorado State University, and also Sandra Ryan at the US Forest Service, though she wasn't involved in this particular study. And I worked closely with Francis Rengers and Jason Keane on this work. They particularly helped with the field aspects of the study, and Diego Panici, a former postdoc of mine on my SCART project and now a colleague of mine at Exeter, did the multi-phase flow modeling that finished off this study and led to the final publication earlier this year. Sorry, had difficulty moving the slide forward there. Just a brief introduction. So my work has focused over the last 10 years on landslide hazard cascades. Initially, I started working on landslides and debris flows in the Swiss Alps, and then on slow-moving landslides in Northern California, on a postdoc in Oregon. And it's since my postdoc at Colorado State University, really, that I've started to think more about the downstream impacts of landslides, or so-called landslide hazard cascades. So yeah, landslides alone kill at least 5,000 people per year, with 2024 being an exceptional year for landslides, according to an analysis in the Landslide blog. But landslides can also cause downstream impacts through sediment delivery. For example, on the right here, we can see the impacts of Typhoon Mangkhut in the Philippines, with a sad, deadly landslide here, which was one of many landslides that fed substantial quantities of sediment into the Antamok River on the island of Luzon, causing a lot of sedimentation, potential future flood risk due to reduced flood capacity. But in my work, I'm really interested in the interactions between landslides and floods during the flood event itself. This can be really hard to actually observe, because much of the evidence of any landslide flood interactions is removed during the flood event. So I'm interested in devising novel tools to monitor and model the dynamics of landslide hazard cascades. So the 2013 Colorado Front Range flood event is an opportunity to actually explore some of these landslide flood interactions. There's really nice pre and post flood event LiDAR that I'm going to show you in the rest of the talk. And yeah, there's also some evidence of landslide flood interactions left behind, particularly in the North St. Vrain catchment that is the focus of this study. So this was a 1,000-year rainfall event in September 2013 that generated a 200-year flood in multiple catchments along the Front Range, kind of south and north of Boulder. It triggered 1,500 landslides, killed 8 people, and damaged lots of infrastructure and homes. The major impacts were through channel widening. So you can see an image on the top left here of a road in one of the catchments along the Front Range that was just pretty much completely removed at this section by the channel widening during the floods. And also landslides tended to be long run-out landslides in this event. So they had impacts just individually, but also delivered sediment getting connected to the fluvial system with impacts such as the ones I'll show. There's a large body of work that shows how channel widening is related to increases in sediment supply over long periods of time, but we didn't find many examples of studies that could show clearly how sediment supply from, for example, landslides into flood events could actually impact flood events at an event timescale. There's also a large body of work that looks into explaining channel flood widening as a function of things such as stream power, vegetation, bank stability, all these other factors. And these studies often find that channel widening cannot be clearly explained by hydraulic variables alone. So yes, in this research, we ask what is the role of landslides in modifying channel erosion during floods. I initially got interested in this topic on this study that I helped Sarah Rathband with. We went into the North St. Vrain several times as part of this study, and Sarah's continued to work in the North St. Vrain ever since. It is a great catchment to investigate geomorphic impacts because it's a largely undisturbed catchment, unlike many of the others up and down the Front Range. It has no road along it. It just has a water storage reservoir at the outlet of the channel that you can see in the images on the right-hand side here. But yeah, no road disrupting the connection between hill slopes and the channel network. So here you can see some snapshots of the DEM differencing I did with the pre and post event LiDAR that was available for the whole region impacted by the flood. So most of the landslides were these long run out debris flow style, feeding sediment into the river channel, and then there was lots of avulsions and bend adjustments causing the channel widening during this event. And overall, this event generated 100 years of erosion when compared to cosmogenic nuclide erosion rates, showing longer term erosion. So during this study, I started to look at the longitudinal patterns, and this wasn't actually part of the Rathburn et al. Study, but this is what got me thinking about the subsequent work I've done in this catchment. So here you can see the longitudinal patterns of erosion shown in the thick red line, channel widening in the black dashed line, and then potential controlling factors such as confinement and specifically stream power in this blue line, landslides in pink along the bottom, and tributaries in black. So as we can see, there is a sudden uptick in channel erosion, which is achieved largely by channel widening. Here you can see of up to 7 times the pre-flood channel width, and this occurs around 7 kilometers downstream. But this doesn't seem to be correlated with any particular increase in stream power at this point along the channel, and it is partially related to an increase in confinement ratio to more unconfined at this point along the channel, but then the channel is also similarly unconfined higher upstream with no associated increase in channel erosion or widening. However, we can see that there's several lateral inputs of sediment, a tributary and 2 landslides labeled L1 and L2, just upstream, kind of 500 meters to a kilometer upstream of this sudden increase in channel erosion. You can see the full DEM of difference of this reach of interest on why I suppose this is probably this is the reach of interest highlighted in this grey bar here, with L1 and L2 highlighted, the tributary highlighted here, and then one further landslide highlighted here. And you can just see that the channel shown in black, the post-flood channel, is not substantially wider than the pre-flood channel shown in blue until around this point just here at 7 kilometers downstream, where the channel widens substantially. So we asked, well, what was the role of these landslides, for example, through damming or bulking the flow of sediment? And can multiphase flow models be used to simulate landslide-flood interactions in this event? So we visited this point along the channel where the channel erosion and channel widening suddenly increased. And this was initially in around 2016. I went down there with Jason and Francis, who'd done some work on some of these landslides and knew of a path down to this point. So we were able to have a nice day out and get down there. And we were nicely surprised to see some remnants of what we hypothesized to be a debris dam just shortly downstream of these landslides, or this major landslide L2 coming into the channel here. You can see this picture is taken looking upstream. You can see the headscarps of some of these landslides outlined in red in this image, and then this bar of very coarse sediment just at this around this point just here. So firstly, we returned with a GPS and went about measuring some high water marks just to quantify what the peak discharge was and whether there was any substantial increase in peak discharge at this point that might be indicative of a dam burst event that would then cause a runaway train of erosion moving downstream and explain this sudden increase in erosion. You can see, I think, Jason and myself here, or maybe myself and Jason, don't know from looking at the back of ours, with the GPS just measuring some of these high water marks around this point just down here. So to estimate peak discharge, to test the hypothesis of a dam burst event, we collected our high water marks with their associated uncertainty, which could be relatively large in the elevation, the Z direction. We returned in 2017 to try and improve this accuracy and ended up using a combination of high water marks collected in both 2016 and 2017 in our peak discharge estimates. We used these in combination with the pre and post flood LiDAR to extract cross sections with which to calculate peak discharge. We use the equations shown on the right-hand side here, and we accounted for the cross-section area uncertainty that came from both which LiDAR we used, the pre or the post-flood LiDAR, with probably the topography during the flood being somewhere in the middle of these two. And we also accounted for uncertainty in high water marks. So for example, in this case, this high water mark has been snapped to the right-hand bank here because it does at least overlap in its uncertainty with the one on the left here. But if that wasn't the case, and for example, this high water mark was further up and didn't overlap with its error bar, say the error bar was slightly higher, we would have considered another cross-section area and used that to propagate into uncertainty in our peak estimate. We used the critical flow method to calculate velocity with the equation that shown just down here. This has been shown to be suitable for calculating peak discharge in this event by John Moody in his 2016 USGS report, where he used a variety of methods for calculating velocity. And this one doesn't require any roughness. So that's made it quite straightforward for us to use this within our peak discharge estimates. To compare with our field and LiDAR-based peak discharge estimate, we also calculated modeled discharge, what we're calling Q runoff, with radar-based rainfall data for the 11th of September, which we consider to be the day, or has been shown to be the day at which soils reached saturation. You can see again from the Moody report in 2016, the cumulative rainfall at various different gauges across the Front Range during this event between September the 9th and September the 16th. And cumulative rainfall really peaked on September the 11th. There was a large uptick towards the end of the day. And a lot of landslides were actually reached around this point towards the end of the September the 11th. We have many landslides observed, and then also modelled discharge shown to peak towards the late hours of September the 11th. So we used rainfall data for this day. We routed it with a 10-meter DEM in Topo Toolbox 2, assuming steady uniform runoff and zero infiltration or storage, which seems appropriate given soils were assumed to be saturated at this point. So although this is a simplistic method, it was easy to apply for a non-hydrologist such as myself, and actually turned out to match the observed peak discharge at the catchment outlet reasonably well, or within the same order of magnitude. So we calculated a peak discharge of 682 cubic meters per second, with the observed being 385 plus minus 80 cubic meters per second. And we were able to use this runoff-based discharge to calculate stream power, for example, in the plot that I showed you earlier. So we then went about comparing our QPeak, our field and LiDAR-based discharge estimate, with the runoff-based estimate to calculate a ratio between the two, which is shown here as C. And this ratio shouldn't exceed 1 in cases of no sediment. It's usually used as a bit of a check of runoff estimations. But a study by Jason Keane in 2016 used this to show amplification of debris flows by sediment and surging of the flows with a ratio of C being more than 1, indicating bulking of the flow by sediment, and a ratio of C of more than 2, indicating a surge in the flow or a possible dam burst event. So as we can see on the right-hand side, you're seeing the channel slope calculated along this 1 kilometer reach, over which we observe this uptick in erosion. We can see the grey bar here showing the modelled dam, which I'll come on to next, and the light grey bar to the right of this showing the dam remnants that we observed in the field. You can also see the landslides highlighted in red here and the tributary in black. So what else can we see? We can see the high water marks shown in black and red for 2017 and 2016 along this stretch of the river. And we can see the pre and post-flood channel profiles showing a clear accumulation of sediment at this point here, where we observed the dam remnants in the field. And mostly I'd like you to focus on the bottom, which is showing the discharge on the left-hand y-axis and the runoff coefficient C on the right-hand side. And we can see that this runoff coefficient is below 1 until roughly the point just downstream of our hypothesized dam, where it increases to a peak of just over 2, which is indicative of a surge or a dam burst event. So we take this to be field evidence of a dam burst event. And this is where I left the study in around sort of 2017, 2018. I then moved to the University of Exeter and started working on my SCARP project, and Diego worked on this project for a little bit as a postdoc. And I'd long been curious about these multiphase models, and in particular I'd heard a lot about Arva flow, which is likely familiar to many of you because it's now been used quite widely in the literature to look at cascading hazard chains. But as far as we're aware, this is the first study to use this model to look at landslide-flood interaction during a sort of individual flood event. So it's an open source model, and it's multiphase, meaning that it considers the solid and fine solid fractions as well as the fluid in a way that traditional flood models can't. And it's really the interaction between these phases, as I will show, is really key to simulating and explaining geomorphic impacts of floods in regions with large lateral sediment supply. So Diego conducted the modelling, and here we can see the 2 steps of the modelling, the dam formation on the left and the dam removal on the right. So we can see the dam that's highlighted in red here that's built up just at the bottom of the landslide, and then in the subsequent part of the simulation this is removed, and the pattern of erosion downstream is truly generated with these deep reds signifying erosion. And here we are seeing on the left the overall topographic change simulated by our overflow. So even after removal of the dam, we can see some sediment still remains there, and we can see the pattern of erosion downstream, matching what we observe in the field. And what's really striking is comparing this to no landslides simulation, where there's no dam build-up, no remnants of a dam, and much less erosion along the river channel downstream. So we think this is compelling evidence of the role of landslides in generating this observed pattern of channel erosion through damming the flow, and then in the removal of this dam, bulking of the flow and making this more erosive, generating the pattern of erosion seen. Here I'm just returning to the study I mentioned at the start where we reproduced this methodology in the Philippines, where there were also a significant number of landslides triggered by a typhoon event, Typhoon Mangkhut in 2019, and significant deposition at the outlet of the channel. This is a mining region, so this is actually accumulated sediment behind a large tailings dam. But we saw other examples of ephemeral landslide dam buildup and failure, similar to our study in Colorado, though those aren't shown on this particular schematic here. But the reason I wanted to return to this is because we've shown that this method is useful for other regions, confined mountainous regions with high natural sediment inputs. A particular output from this study was the fact that in a big sensitivity analysis that Diego conducted of many different model parameters, internal friction, rheology, drag coefficient, control, this is a control run here, the main factor that he found to be the model sensitive to was rheology. So I think this is a run here where he hasn't included the fine sediment fraction, and this is the only run that doesn't do such a good job of simulating the observed channel widening and geomorphic impacts. So yes, in Colorado case study, in fact, only coarse sediment was needed, not the fine sediment. So this just shows how the model kind of reflects the geology of the two different regions. It's not surprising that fine sediment was needed in this region in the Philippines that's heavily clay dominated, whereas in Colorado we have a very crystalline geology in the Front Range and in the North St. Vrain catchment, which makes sense that we would only need coarse sediment within that simulation. Another big take-home message from this study was that the model was not sensitive to a plus minus 20% discharge variation that we were asked to perform by the reviewers. So actually that was really helpful to have to go through that review process and have to do those extra sensitivity tests, given the highly uncertain discharge and complete lack of observations of discharge in this region as compared to Colorado. And it showed us that the model wasn't sensitive to plus minus 20% discharge, really highlighting the role of phase interactions between the solid, fine solid and fluid fractions in simulating geomorphic change. Given all the mining activity in this region, the links between landslides and channel widening were less clear than in the Colorado study, due to things like diversions that divert some of the water away from the main channel and make it impossible to completely model what's going on. But we still have some useful outputs from trying this approach in this particular region. And you can find the study by scanning this QR code here. So in conclusion, I've shown the first applications of the multiphase flow model R-over flow to landslide flood interaction. Landslide sediment delivery was critical to simulate patterns of channel erosion during flooding. There was an ephemeral landslide that built up, ephemeral landslide dam, rather, that built up during the flood event and was removed during the flood event. And in fact, we wouldn't really call this, based on the simulations, a dam burst event. The bulk of the sediment was removed in the first few seconds, and then sort of more gradually over a few minutes. So we're more referring to this as a dam removal or dam failure event. And this bulked flow with sediment, making this more erosive and generating the observed pattern of channel widening downstream. So we suggest that landslide channel interactions are a crucial factor in flood risk assessment in confined mountain catchments, and that you have to consider sediment to fully simulate geomorphic impacts of floods in these regions, and that multiphase models such as R-Flow are useful for simulating sediment charged flows, such as that observed in the North Saint Vrain. I was presenting at EGU the other week, and someone asked me a question at the end. I think he was involved in an insurance claim where it was important to define an event either as a flood or a debris flow. And I think that studies such as this and lots of work on these, what I'm calling sediment charged flows around the world now, are showing that often these flows transition between different phases, and it's really difficult to classify them as one thing or another. So that's an interesting take-home message as well. I think I've overrun a bit, so sorry about that, but thank you very much for your attention, and I look forward to having feedback from Francis and the webinar organisers and any questions you might have by email. Thank you. Bye.
Great. Well, thank you, Georgie, for that great talk. I hope everyone saw it finish. It seemed like we had a little bit of out of syncness. Well, we will now move on to Francis, who's going to be talking about a catchment a little bit north of where Georgie was presenting on. So take it away, Francis.
All right, so here, let me get this going. Okay, so hopefully everybody should be able to see this. I'm just going to, kind of follow on a little bit what Georgie was working on. Here we're going to talk about another study in the Front Range where there's this debris flow river interaction, and we're going to mostly focus on this a small debris flow catchment and kind of looking upstream of there. So this is going to be looking at debris flow deposition, where and why it happens. So I want to talk about this debris flow that was triggered in the Black Hollow watershed, which is located in the Cameron Peak fire. Debris flow occurred on July 20th, 2021, and that was about 11 months after the fire. And unfortunately, there were 4 fatalities resulting from this debris flow. And when you look at it from this angle, you can see that not only are there a lot of coarse sediment, large boulders on the fan here, but there's also a lot of woody debris, and it impacted the Cache la Poudre River, which it feeds into. So this partially dammed the Cache la Poudre River, and it sent a lot of ash and suspended sediment downstream. So today we're mostly going to be focused on what's happening upstream of this fan. But the ash and suspended sediment from that debris flow actually were really impactful. That caused a fish kill for more than 100 kilometers downstream. So this debris flow had a lot of negative impacts. So we ended up using LiDAR and DM of difference paired with field mapping to investigate the debris flow volume, as well as specifically deposition within the catchment. Here's a little timeline of the LiDAR acquisition. So the Cameron Peak fire actually started mid-August, August 13th of 2020. And there happened to be a LiDAR collect of the Black Hollow watershed in August 30th of 2020. So we had a fresh collect then. And then that next summer, there was the Black Hollow debris flow. And we were lucky enough to have another LiDAR collect just a few months later. over Black Hollow. And so we have a fairly tightly constrained topography of this debris flow event, which is really unique. Here's an image, satellite imagery from after the fire, but before the debris flow. You can see a little snow on the hillsides there, but I want to show you that most of the sediment that was involved in this debris flow really kind of originated from the channel. So you can kind of see when I toggle back and forth between these images that after the debris flow, a lot of sediment was recruited from the channel. And then when we look at the LiDAR difference, you can see in the red colors, that's erosion, blue colors is deposition. And there's a little bit on the hill slopes, but most of the activity is in the channel. So we're going to really focus on the channel activity today. So I'm going to start with kind of a top line result from the LiDAR difference. This kind of motivates everything, which is that when we looked within the channel itself, this is upstream of that debris flow fan, we saw that there was 136,000 cubic meters of erosion, but there was also 29,000 cubic meters of deposition within the channel. So before it even reached the fan. So about a fifth of the sediment that was eroded actually redeposited in the channel before it even reached the fan. So the fan and then subsequently into the Poudre River only saw about 100,000 cubic meters of sediment. So the main study goal here was to explain what controls deposition upstream of the watershed outlet. So to poke at this a little bit more, we're going to look at 5 contributors to in-channel deposition. So prior literature has shown that tributary junctions tend to be a place where you might see sediment deposits. Also, wood jams or can frequently induce deposition of sediment. We also looked at the entrenchment ratio. This is basically a ratio of the channel width to the valley width. We looked at sediment stored on bars and also how channel slope affected sediment deposition in this debris flow. So this figure, we're going to kind of keep coming back to this. This is going to be our anchor figure. And this is going to show us what happened in terms of erosion and deposition in the channel. So let me walk you through it. On the x-axis is distance from the outlet. So 0 is where the fan is of the Black Hollow watershed. Then on the y-axis, we have change. So positive change, deposition, is in blue. Negative change, erosion, is in red. And we were able to compute this change from the LiDAR data using Lauren Guido's new tool called Incremental Debris Flow Volume Analyzer. And what that does is it makes up equal area spaced polygons all along the channel from upstream to downstream, and they're spaced about 10 meters apart. So we're going to look at those 5 contributors and see if they can explain some of these depositional areas. And we're going to also look and see if anything can kind of help explain some of the erosional patterns as well. All right, so getting into it, first contributor, tributary junctions. So we took the Black Hollow watershed, broke it up into these sub-watersheds. And so you can kind of see those yellow dots at tributary junctions. And we looked to see, do we see any large deposits at those tributary junctions? So coming back to our anchor figure here, in the dashed lines, you can see the locations of those tributaries. And for the most part, you see that those dashed lines don't tend to line up with any of the large blue deposits. Now, there is one around 3,800 meters from the outlet where we see it kind of aligns with the blue deposit. But if we look at the photo, so here's a photo of that location. You have a tributary coming in. You have a pile of sediment here in the foreground in the main channel. But when you look in map view at the DM of difference, what you actually see is there's a little deposition upstream of the tributary, and then it's actually kind of an erosional reach where it meets the main channel. And instead that deposit is sort of on the inside bend of the channel. And so I'm going to get into this particular location a little bit later. But we don't think that's because of the tributary necessarily. We think it has more to do with the bend and some channel widening that's happening there. So major conclusion from contributor one is that tributaries don't seem to be depositing large fans. So that's not our big culprit. So the next thing we're going to look at is wood jams. So here I'm going to use two words, wood dam and wood jam. And wood dam, I'm going to use that when wood completely crossed the channel and formed a dam that would have stopped sediment and slowed down water. So it's a channel spanning feature. Wood jam, I'm going to use that when it's off to the side of the channel. So when you look at the photo here, you can see there was a dam break, and when we looked at this in the field, you could see wood pieces that span the channel and were broken. So we're pretty convinced this was an actual dam that formed and then broke. And if you look to your left, you can see the dam of difference here. So the shaded relief shows the topography, and you can even see some linear features where there are some wood pieces in there. I kind of made a custom hillshade to be able to show that. The blue represents deposition, so there's a lot of deposition upstream from that wood dam, and then behind a wood jam a little further. And then the red shows the erosion that happened downstream of that dam break. So what we did is, using locations that we mapped in the field, we were able to estimate the wood volume from LiDAR, and those are shown as stars. So that volume is shown on the y-axis here on this plot. X-axis is, again, distance from the outlet. And here we've labeled where the wood dam break occurred. Upstream, we've shown the volume of deposition that's upstream of all the wood jams. And then downstream, we've shown the erosion. And what's interesting, downstream of that wood dam break, we see a large amount of erosion. So note that there's a log scale on the y-axis there, and more than half of all the erosion happened just downstream of that wood dam break. So we think that wood dam break was pretty important for the debris flow as a whole, and may have kind of really accentuated the sediment that was scoured downstream. So if we go back to our anchor plot here, now we have these gray bars that show the locations of the wood jams that we mapped in the field. So we didn't force the locations of these gray bars based on the dam of difference. We really let the field observation show us where those were, and then they align quite well with several of the deposits. So it looks like wood jams explain deposits fairly well. So now let's look at the third contributor, entrenchment ratio. So this is the ratio of the channel width to the valley width. So if you can imagine a channel that's exactly equal to the edges of the valley, that's going to be 1. But if the active channel is really underfit compared to the valley, that's going to be a much smaller number. And so we calculated that along cross sections for the entire channel using both the before and after LiDAR. And I just want to show you what the dam of difference looks like in a couple of these places. So you can see in one place it goes from 25 meters to 64 meters, and there's lots of deposition as the channel kind of expands to the edges of the valley. And then another location, it goes from 40 meters to 76 meters. And again, the valley's expanding, and as the debris flow comes down, it's expanding to match the edges of the valley, even though pre-event, the channel was smaller. Here's what it looks like from the field. Here's a photo that I took. This is one of those areas where at this location, it's about 40 meters, what you can see in the photo. And I placed the 4 meters over on the side where the original channel was. So you can see that when the debris flow came down, it really expanded as the valley widened, and it was able to deposit some sediment. And then here's our interesting channel bend again. We have a tributary coming in from the bottom. It just so happens that also is an area where the encroachment ratio is changing, and the channel was expanding to fill out the valley. So I think that expansion kind of helped with that deposit, as well as obviously the bend in the valley kind of helped to slow down sediment and encourage deposition. So if we go back to our anchor figure here once again, now we've added some green bars on the top, and we've added a new plot on the bottom. So the green bars are just those 3 locations where we saw a really big change in encroachment ratio before and after. And so if you look at the bottom plot now, we have a pre-event encroachment ratio and a post-event encroachment ratio. And so that in those 3 locations, we see a really big change in from before to after the debris flow. So now we'll look at a 4th contributor here, channel bars. So we see lots of deposition in these small bars. Here's a photo that kind of gives you an idea of what one of those bars looks like. And then looking at the DMF difference here, you can see these blue areas of channel bars. They're not all that big, and they're not exactly the same as what you would see in a typical fluvial setting where you have erosion on the cut bank and deposition on an inside bar. This is more alternating bars, but we did want to investigate the role of sinuosity because we thought, well, maybe bends in the valley might influence where we see bar deposition. So if we go back to the anchor figure, we have now added this kind of yellow area in the location where we saw a lot of bars in the field and in our DM of difference. We've now added a 3rd plot to the bottom here. So you can see in orange, we mapped sinuosity along the channel, and interestingly, our kind of green bar, that interesting bend where we see a deposit, it does match up with a peak in sinuosity. But in general, it doesn't seem like the sinuosity tends to quite explain where we're seeing bars. So bars here are a little bit more mysterious and probably just represent some changing flow dynamics, where as the debris flow moved downstream, there was just an opportunity for deposition. The last contributor to in-channel deposition we're going to look at is channel slope. So here's a deposit that I took a photo of in an area where the local slope was a little bit low. And I think this may even be the best. Some of this deposit might be related more to fluvial processes because we kind of see some of the sediment looks more imbricated. So this might be something that happened more at the waning tail of the debris flow where it was more water dominated. So we went ahead and plotted a few areas in the field that looked like none of the other things were contributing to deposition, but they did have a locally low slope. So we plotted this in teal. So you can see that up on our top anchor plot again, and then on our bottom plot now, we've also plotted slope alongside sinuosity. You can see, those teal bars do line up with areas of local low slope, but similar to sinuosity, slope doesn't seem to be a really defining morphological feature that's going to be super prescriptive in indicating ahead of time where we might see deposition. So in terms of results here, we see that, overall, there was mostly erosion happening in this channel, which makes a lot of sense. But there was a decent amount of channel deposition, and even more channel deposition than we actually saw on the fan. The rest of that got pumped into the Cache-la-Poudre River. And if we look at a pie graph here of the different types of deposition, we see that the change in entrenchment ratio actually accounted for the majority of deposition. So even though we only saw a really big change in entrenchment ratio in about 3 spots, that accounts for a little over 50% of all the in-channel deposition we see. And then the runner-up there were wood jams. That accounts for about 25% of all the deposition we see. And then the rest of the deposition we see on bars and due to in areas with a lower slope. So just a couple takeaways to wrap up here. What's interesting about entrenchment ratio is that's something that could be calculated in advance. So if we look at our plot here again, we have this black bar plotted at the bottom, where it's sort of a threshold. And we noticed that when the entrenchment ratio was about 0.07, that seemed to be the locations where we saw the most amount of deposition. So obviously this might change from region to region, but that's something that could be calculated in advance, and it could give you a little bit of a heads up if you were interested in an area that you were particularly worried about sediment deposition in. The second takeaway here is that wood jams, and we may be able to calculate this in advance, but I'll kind of walk you through what that might look like. So we had a previous study where we looked at wood jams and noticed that where you see wood jams, you see a lot of sediment storage, so they're really important. And there's this ratio of the wood length to the channel width, the length of wood L over the channel width W. When that ratio is between about 0.25 and 1, that's where we see the most deposition. And what's interesting is using LiDAR, we can actually calculate tree height, especially in these areas with conifers. It's actually fairly easy to identify the top of the trees. So in our case, we had a median tree height of about 9.6 meters. So I just kind of looked along the channel to see what that tree height was, and then that was our median. And so I calculated that ratio, and I was a little bit conservative, and I just said, hey, if we look at a lot of cross sections every 10 meters down the channel, how many cross sections have a ratio between 0.5 and 1 if we use that median tree height of 9.6? And about 58% of them did. So I think the takeaway here is that may not tell you where, wood jams are going to happen exactly, but it does tell you, hey, wood jams are very possible in this region. So that's something you could do ahead of time to just basically say how prone to wood jams might my channel be. And then just really briefly, I just want to show that, we did a regional comparison. We looked at the total volume of known debris flows divided by their watershed area. So studies in Southern California are in blue, Colorado is in orange, and Utah is in red. And you can see that this study, even though it produced a lot of sediment, 100,000 cubic meters is quite a lot. When you divide it by the watershed area, which is 17 square kilometers, the actual yield is not that large compared to places like Southern California. But it does kind of fit a regional trend, which is useful. So in conclusion, unlike some post-fire debris flows that we've seen where it's mostly erosion in channels and then it doesn't deposit till it hits the mountain front, in this case, there was a large amount of in-channel storage. About a fifth of the total erosion ended up being redeposited in that channel. And the main driver here was the encroachment ratio that contributed the most to in-channel deposition. Wood jams were also a really important key to the deposition. And at least in one case, a dam breach seemed to really exacerbate the downstream erosion due to debris flow. So I will stop there and take any questions.